So the way we model dielectrics is that in the medium itself, we assume that there are dipole densities in the medium, even in free space. And this dipole density leads to something called polarization. And then we finally figured out a way to tie this polarization, right? Polarization is just dipole density. So dipoles each have units of Coulomb meter. They're distributed over space, meter cubed. So this gives me Coulomb over meter squared. This gives me the same units as the flux density. And we said that leads us to propose that the flux density is a kind of polarization in free space. Okay. And then we wanted to go back and tie this polarization to the fundamental postulates of electrostatics. Div E equals rho and curl E equals 0. And the only entry points we see is the charge density. So we asked ourselves, is there a way, if we have this medium and it's polarized in some way, is there a way to show what would the charge distribution be, the bound charge distribution be due to this polarization? And here, this polarization we're talking about is the polarization of the bound charges in the material. So we differentiated between two kinds of charges that could exist in space, free and bound charges. And we said free charges are our classical charges that we're aware of that can move, charges that appears on matter, while the bound charges in the context of the model of electrodynamics is assumed charges that exist at every point in space and that cannot move from one point to the other. It's like, imagine them to be some charges stitched into the fabric of space itself. Those charges cannot move from one point to another, but they can stretch and orient themselves. And of course, we know that free space is not charged, so there has to be an equal number of positive and negative charges. So in free space, as a medium, space itself is not charged, but space has dipoles because it has an equal number of positive and negative bound charges, and those stretch and condense. And this gives rise to polarization or dipole densities. Okay. And then, the last thing we did towards the end of the lecture is here we want an entryway into the postulates. So can we tie the polarization to a charge density due to polarization? You have some material and polarizes in a certain way. Would this give rise to a charge density? And the way we approach that is through the advantage of deriving the voltage due to P, right? So we derive the voltage due to P at every point in space, and then we compared that due to the equation with the equation of the force voltage due to a charge density, and then we arrived at this result. We arrived at, let me see, where is the result? Okay, we arrived at this interesting result. We said that the charge distribution that appears in the medium, in this case free space, or any medium really, due to polarization, is the polarization dot r hat over r. This is the bound charge density. Okay, so this is the ultimate. We did an integration and whatnot, and this is the result that we got. Okay, so this ties polarization to charge density due to bound charges. If you think about that, like this is space, right? So say you're interested in the charge density here, dV prime, charge density here. What's rho PV at this point, right? So the idea here is that you pick any point in space, any random point, P. And then there is a distance to that random point, R, and then R hat, right? And then, and the interesting thing here is that it doesn't matter where P is. P can be anywhere in this in the medium. So when you do this and you do this calculation, you take P, you know P at this in this point. So I know P here, the polarization here. So you take P, you dot it with R, right? And you divide it over R. This gives you the charge density. It's an interesting result in the sense that the point P does not matter, right? Where it is, right? So, but still, this is not a really very intuitive result, right? So we would like to kind of improve or refine this result a little bit. Plus, it's not complete because if we have a medium and then we have polarization, some charge density due to the polarization will appear on the surface, right? Because you're going to have the dipoles kind of oriented towards the surface, right? And there will be nothing here, right? Na, right? So you should have some charge density naturally appearing on the surface. So we don't know what the charge density on the boundary is yet. So this is not complete. So we have to kind of refine this a bit. So let me rewrite the voltage that we got. So the voltage at the point P, by the way, this is how we got this. We got this from the equation of the voltage. The voltages are at point P, this random point, any point, is 1 over 4 pi epsilon naught, integration over the volume, P dot R, or let me go back. I think I have it here. P dot R hat, sorry, over R squared dV prime. Okay. And this is how we tied it with the charge density, because we ask ourselves, what is the charge density that's going to give us the same voltage? And the charge density that's going to give us the same voltage is P dot R hat over R, right? From the equation of voltage due to charge density. This is how we tie between the two. We need to refine. We're not satisfied with this form. We want to see if we can get a better form. So we need to improve this a bit. So one thing we can notice, we can ask ourselves here in this problem, 1 over R squared, R hat looks like something. It looks like divergence. It looks like gradient of 1 over R in spherical coordinates, doesn't it? What's let me just review gradient of a scalar field U in spherical coordinates, delta U over delta R, R hat, sorry, minus 1 over R, right? Well, let's do gradient 1 over R. Let's see what that is, right? And then plus 1 over R du over d theta plus 1 over R sine theta du over d phi. Right? What's the gradient of 1 over R over spherical coordinates? Well, du over d1 over R over theta is 0, d1 over R over phi is 0, so we don't worry about those terms. We only have to worry about 1 over R. So 1 over R differentiated with respect to R is minus 1 over R squared. Okay, R hat. So notice R hat over R squared shows up here. Okay, so it's somehow tied with this. Here, like a subtle point, for this problem, gradient of 1 over R is actually positive, not negative. Why? Because 1 over R is the distance from point P, right? So from this context, I mean, in general, your origin is at point P because you're integrating everything, and R hat is always pointing to point P. So from the context of spherical coordinates, the R hat that we're used to for spherical coordinates actually points in this direction, spherical, R hat spherical. But our R hat for this problem is always pointing opposite to the R hat from spherical coordinates. So when we apply this, here we're applying the R hat of spherical coordinates. So this is opposite to that. So this will cancel the negative sign, okay? The point is the one we can take this R hat over, sorry, we can take R hat over R squared. Instead of that, we can write P dot gradient 1 over R dV prime. Okay. And now we can use one of the product rules from vector calculus. Remember, we talked about some of those, and we said we're going to use them later, which called the Leibniz rule, Leibniz rules. So one of the products rules is as follows. I'll write it down. It's gradient of a scalar field multiplied by a vector field, meaning you take a vector field, you scale it differently at every point in space. So this is some kind of product rule, right? So we said this equals the same scalar field times the divergence of A plus, so the first one times the differentiation of the second one, plus the second differentiation of the first one, which is the gradient of phi. That's the only way you can differentiate a scalar field, dot A. Okay, so this is sort of product rule. And does it make sense? Well, yeah, scalar times vector is vector. Gradient, the divergence of a vector field is a scalar. So this right side, left-hand side is a scalar. Is this a scalar? Yeah, this is a scalar. Divergence is a scalar times a scalar field is a scalar. And dot product gives me a scalar always. A vector field times a scalar times a dot of vector field gives me a scalar. If your right-hand side gives you a vector and then your left-hand side gives you a scalar, something is wrong. You have something wrong along the way. Okay, so the point is now we can use this. You can use this to rewrite this equation. So that we can, how can we use this? We can say that P, well, let me rearrange this. I can rearrange this as gradient phi dot A equals divergence phi A minus, take this to the other side, phi gradient A. I can use this now to rewrite this. So I say now P dot gradient 1 over R equals what? So the scalar field is 1 over R. The vector field is P. So this is equals divergence of the scalar field 1 over R times the vector field P minus the scalar field 1 over R times the divergence. Okay. I can take this and plug it back into the integral for the voltage. So the voltage now is going to be, and then I can you know, separate the integral into two integrals for each part, right? So this is going to be 1 over 4 pi epsilon naught integration over the volume of divergence 1 over R P. This is nice. I'm integrating a divergence. I can use now the divergence theorem. And then 1 over 4 pi epsilon naught V prime minus 1 over R, okay, dV prime. So here I can use the divergence theorem. So what does divergence theorem do? It turns a volume integral into a surface integral on the boundary. So this is going to be 1 over 4 pi epsilon naught, a closed surface integral over the boundary of the medium, right? And then it's going to be there's going to be 1 over R out. I can take it. It's a constant, right? It's going to be, so over the boundary, what matters is the what only contributes to the integral is the normal component of the field at the boundary. So it's going to be P dot n hat ds prime. So here I'm integrating over the boundary. Essentially, instead of writing ds prime as a vector, I took n hat out to represent the direction of the boundary. And then the R is just P is just scaled by R. So that's where R comes from. Okay. Plus the second one is the same. I can't do anything with it really. Minus. Okay. So this is on the boundary. What does this look like? This looks like a voltage due to a surface charge density, right? Because this looks like this is like a surface charge density divided by R integrated. You get the voltage. This is, if you go back to the voltage equation from a surface charge density, this looks exactly like it. This looks like the voltage equation due to a volume charge density. Okay, so this looks like a voltage equation due to a surface charge density. This looks like the voltage equation due to a volume charge density. So this tells me that the corresponding charge density due to polarization at the boundary is actually P dot n hat, and then the charge distribution in space due to charge volume charge space due to polarization at every point in space is minus divergence P. This now is a much more useful equation relating the polarization to the charge density. This is easier to work with, okay? Right? This is easier to add to the fundamental theorem postulate because the fundamental postulate also has a divergence. Okay, so if you go back to the axiom says that divergence of E equals rho over epsilon naught. Okay, let me restate. So this is given to you as an axiom, but let me show you what is this result. This is a deep result. Okay, let me tell you what it is saying. It's saying we can write the axiom actually differently. We can say what fundamentally the first axiom is saying is that in space we can assume has polarization. Space can be polarized, essentially. That's what we're saying. But what we're saying, we have, okay, space can be polarized, free space. Okay, that's one. Someone can come and tell you, knocks on your door and says, hey, space can be polarized. You say, fine, but we've never seen evidence that space can be charged, right? Empty space, there is no evidence that empty space is ever charged, right? Charge comes only from matter, it doesn't come from space. So, okay, so then someone can reply, okay, that's fine. Space can be charged, but the net charge will always be zero. Okay, so free space is charged, has a net infinite amount of a lot of positive and negative charges that are always equal, so that we don't see a net charge coming from free space. But even if there's no net charge, space itself, due to those equal positive and negative charges, can be polarized. But the rho PV is always zero, except if you have some free charges. If you have some free charge due to matter lying around, then this free charge is going to interact with the space charge and is going to cause it to charge negatively, so that the net charge is always zero. So the free charge is going to equal the negative of the polarization charge, and then we know that the polarization charge equals grad minus grad P. So this is going to be minus dot grad P, right? This is the first postulate. P, we called it D, right? So D is the polarization of free space. And then we tied D to E by saying that a field E, a force field E, multiplied by some proportionality constant gives me the polarization. That's essentially the first postulate. So really D, we can look at D as the polarization of free space. That's how we interpret D. E is the field intensity, right? Essentially, it's the force field due to the electric field. What if you put a test charge, what force this charge feels? And then D is a measure of the polarization of free space, assuming that assuming that space can be polarized, and this vector E, as field E, is going to polarize space. The amount of polarization is D. But that's fine. So there is an epsilon naught here. Okay. That's free space. But now the nice thing here, now we can include the effect of material, because free space and this theory can be polarized. That's fine. And it's boring. I mean, there's no need for it because D is proportional to E with their constant epsilon. It's always that same epsilon. So why do we care about D and E? We care about D and E because now we can put in effects of materials, model effects of materials, because material also can be polarized. If I have like some here, some wood or whatever kind of matter, it has atoms in it, and the atoms in it also can be polarized. So this sort of polarization that is extra to the polarization of free space. Now we have a way of incorporating this into the theory, because we know that divergence in the polarization of the material is going to lead to a volume charge density. So I can add this always to this theory here, plus rho PV. So this is assuming we have some material, it's not free space, right? And now I can take this to the other side. So I can rewrite this as grad epsilon naught E, right? Minus rho PV equals rho V, right? And this we said is D. This is the polarization of free space. Well, let's not call it D at this point. Rho epsilon E is the polarization of free space. If we are in free space, D equals epsilon naught E. If we are not in free space, D does not equal epsilon naught E. Epsilon naught E is just the polarization of free space. When you have material, you have an extra polarization due to the material. Okay, so we want to now use this result. So this is going to be divergence of epsilon naught E minus plus divergence of P equals rho V. Divergence is linear, so I can write this as divergence of epsilon naught E plus P equals rho V. So what this is saying is that the divergence of the polarization due to free space plus the polarization of the dipoles in the material equals rho V. This is what the first postulate now says. And we've naturally incorporated the material effects. Okay, we could stop here, but we want to go further. And the way people go further is so the material is here, right? This is some wood or some glass or whatever, and there's a field E. We could ask ourselves, how does the electric field polarize the material? I mean, it could be complicated. It could depend on the strength of the electrical field and the direction. The simplest way to write it down is that saying that, hey, the dipoles in the material are going to orient themselves. Assume they can move such that they can orient themselves with the electric field in the same direction of the electric field. And their strength is going to depend how much they stretch. It's going to depend also on the strength of the electric field. So we can say that maybe the polarization in the material, and this maybe happens most of the time, is just some proportionality constant is the same as the, so how we write it is that it could be the same as free space, by the way. So it could be the same as free space. So it could be epsilon naught E, but it could be different than free space. The way we encode that is by including what's called the electrical susceptibility. So this constant is called the electric susceptibility. So essentially, this encodes how strong does the material polarize. If CE is 1, this tells me that the material polarizes the same as free space. If CE is 10, this material polarizes 10 times more than free space, essentially. So this is how you encode how you relate a polarization to the electric field. You assume that the polarization is going to be in the same direction as the electrical field, and is going to be proportional to the electrical field. So this is more useful to assume that. And if we plug that back in, we get grad epsilon E plus epsilon E0 phi E equals rho V. And then we can take E out. So this becomes grad epsilon 1 plus V CE E equals rho V. Now this whole thing is the total D vector. It's the total polarization. So D, the total polarized field, is the polarization due to free space plus the polarization in the material. This is essentially what we're saying. So this equals epsilon naught 1 plus ZE E. This thing is called relative permittivity. This whole thing is called the permittivity of the material, right? So in more general sense, we can say D equals epsilon E for a material. And where does epsilon comes from? Epsilon comes from epsilon naught plus Z. Z is a susceptibility. If we take 1 plus ZE, which is unitless, it's just the relative. So we say epsilon is epsilon R, epsilon naught. This is what's called relative permittivity. Okay. But essentially what D in general material, not just free space, what D is encoded, D is a polarization vector. And it encodes, within it includes the polarization of free space, right? So this includes the polarization of free space, epsilon naught E, plus the polarization due to the material, which is epsilon naught E times the susceptibility E, right? So this is polarization due to free space of polarization of free space, and this is polarization of the material. This is the model that you have to be thinking of when you're thinking of dielectric materials. Right, this is what everything here means, and the way now it all now lumps back down to a number, a single number that we can use to model dielectric materials, and that single number is epsilon. Right, for air, epsilon is epsilon naught because epsilon R is 1. For some other material like wood or I don't know, glass or whatever, or plastic, epsilon will be different. Paper, okay. All right. So I want to now investigate this further. I want to go. I think there's we want to refine the classification. So I want to talk about how can we classify dielectric materials. Right? Because I said essentially the model for dielectric materials is D equals epsilon E. The polarization of free space plus the polarization of the material depends on E using this constant. The question is, does this constant is the same in every point in space? Does this constant vary with respect to direction? Is this constant linear? Right? So this kind of like the nature of this constant gives you the type of the dielectric material. So we kind of like want to talk about classification of dielectric materials. And the classification depends on the behavior of epsilon. So we can classify materials as linear. So we can say the material is linear. What do we mean by material being linear? It means that D equals epsilon E. It means that E does not depend, epsilon does not depend on the strength of E. Essentially, that's what it means if the material is linear. E does not depend on E, essentially. Epsilon does not depend on E, meaning the polarization always has this linear formula. If the field is stronger, epsilon does not change. So the way we do that, we can plot magnitude of D versus magnitude of E. It's always going to be, the slope is always going to be constant. It's always going to be epsilon. Right? The material does not behave like this, where it does something like this, where the polarization tapers off as E increases. No, the more electric field you put in, the more polarization you get. It does not taper off, right? This is really common. It's common for electric material to be linear. Magnetic material, however, when we talk about magnetics, we're going to see that is typically not linear, Magnetic materials can saturate, right? So that's why capacitors don't saturate while inductors saturate, right? However, capacitors break. So although the linearity is maintained for electrical material, typically electrical material is mostly linear, meaning the ratio between D and E is always constant and equal to epsilon. However, materials do break. So after a certain electric field, the whole material is going to break. The dipole is going to just, disconnect, and the material is going to ionize, burn, or whatever, right? Turn to plasma. Right? So electrical materials tend to break rather than saturate. Magnetic material tends to saturate, right? So that's one property. Linearity, and most electrical material, dielectric material, is linear. Linear up to a point where it breaks. We're going to talk about breakdown in a bit. The other property is homogeneity. So we say that the material is homogeneous. Means same epsilon everywhere. If I have a crystal of diamond, let's say, epsilon is going to be the same everywhere. It's not going to depend on the position inside the crystal. So when the material does not vary in space, epsilon does not depend on space, d epsilon over dx equals 0, where x here represents a point in space. So we say the material is homogeneous. So most materials are homogeneous. The final property is isotropy. We say that the material is isotropic. Say you have a crystal, some material, and the E field is facing this direction, or the E field is facing this direction. If epsilon depends on the direction, varies with the direction of the electric field, then we say that the material is not isotropic. But if epsilon is the same regardless of the direction of the electrical field, doesn't matter where the electrical field is coming from, what direction it's coming from, epsilon is going to be the same, then we say that the material is isotropic. Most electrical materials are isotropic, except some materials. There are some weird crystals that are not isotropic. Meaning, if I shine the electrical, I'm using a light analogy. If I point the electrical field, apply the electric field in some direction, it will polarize differently than applying it in a different direction. So there are crystals that exist that are not isotropic, but most materials are isotropic. So this is the concept of simple material. Most electrical materials is simple. So a simple material, and I'm going to just apply a lot of jargon here, but now you understand the jargon. So a simple material is linear, homogeneous, and isotropic. Okay, and most dielectric materials can be assumed to be linear, homogeneous, and isotropic. Okay, the only thing that we haven't talked about is dielectric strength, and the idea is simple. The idea is that I have material, I apply electrical field E. I can make E equal 1,000,000 volts per meter, 1 trillion volts per meter. Will the material continue to polarize regardless of the field strength? No. I'll reach a point where the field gets strong enough to break the dipoles in the material. The atoms themselves break, and you end up with electrons flying freely, right? When you reach such a state, the maximum field you get for such a state is called dielectric strength. Dielectric strength. So different materials have different dielectric strength. Some materials can tolerate larger electrical fields, and some materials don't tolerate a lot of electrical fields. there's table 4.2 in the textbook. Let me see. I can get to it. Come on. Where's the textbook? Table 4.2, I believe. Okay, dielectric strength. Oh, this is a problem, sorry. Okay, so if you look at table 4.2, it shows you the dielectric strength for different kind of materials. So for example, for air, it's 3.6 to the power 6 volts per meter. So what this tells you, if you have a field stronger than this, air is going to turn into a plasma. The gas molecules of air is gonna separate, and you're gonna have a plasma. You won't have a dielectric material anymore. The dielectric material is gonna break down. If you have a PCB board, for example, and it's in air, right? So that tells you that you cannot have more than 3 million volts at a distance of 1 meter. What about centimeter? What about millimeter? So millimeter, so you have to kind of take this volt per meter, right? So a meter has 1,000 millimeters. So it's going to be 3,000 volts per millimeter. So the dielectric strength in volts per millimeter is going to be 3,000. That tells you, if, like, let's say you're doing a PCB board. If you have two conducting surfaces 1 millimeter apart, the voltage between them should not be more than 3,000 volts, or else you're going to get arcing between those two conductors. Of course, some other materials are going to have a stronger dielectric strength. For example, mineral oil is going to have a stronger dielectric strength. What's interesting here, you notice that vacuum itself, you would think that you cannot break the vacuum, right? And you would think, like, just using the dielectric model for classical EM, you would think that the vacuum dielectric strength should be infinity. It's just vacuum. How can you break the vacuum? Well, it turns out practically you can break the vacuum, but this is not due to the classical theory. This is due to the more advanced quantum theory. So the vacuum is really not actually vacuum. It has stuff in it, right? But notice it's very large. It's like 10 to the power 18. That's like a million. It's like 12 orders of magnitude more than air, right? So it's going to take a stupendous amount of electrical field to break the vacuum, but it is possible to break the vacuum. Not due to classical effects, due to quantum mechanical effects. Okay. Let's see. The next thing we want to cover is interface conditions. Interface conditions. So we understand materials, but what if we have two different kinds of materials connected together? Essentially, what happens at the boundary of materials? So you have material and air, so you have epsilon naught. What happens at the boundary? You have the material, epsilon 1, and then you have some other material, epsilon 2. What happens at the boundary? So that's the next thing that we're going to study. What essentially happens at the interface, right? What will happen to the electrical field as we pass the interface? And given what we know so far, right, summary of what we know about epsilon, we know about susceptibility, we know about polarization, we know how to tie polarization charge density with the polarization vector. We know that rho PS equals P dot n hat, right? How can we use all this to understand what happens at the interface? And there can be two kinds of interfaces. There can be interfaces between two dielectrics, epsilon1, epsilon2, and then there can be an interface between a dielectric and a conductor, epsilon, and then conductor is not dielectric. So for the conductor, epsilon is going to be epsilon naught, because the conductor does not polarize, right? So there's only going to be the free space polarization. So there won't be an epsilon for the conductor. It's going to just be epsilon naught. But however, the conductor is a different kind of material, right? It has free charges, infinite amount of free charges. We already covered this. So we've already done this. Now we want to do this, okay? What we need to do is we need to do the postulates, apply the postulates at the interface. So let me expand the interface. And then I need to understand, so this is epsilon1, epsilon2. I need to understand if we are really close to the interface. So just before the interface, here I have E2. And just after the interface, I have E1. And we can assume that the field is discontinuous. The question is, how does the field vary across the interface when we move from material 2 to material 1? So what we can do is we can decompose the field into a tangential component, E1t, and E1n. So just after the interface, we can decompose the field after the interface into a tangential component and a normal component. And just before the interface, we also divide the field, decompose the field into a tangential component and a normal component. And we study each of those separately. We study how the tangential component of the field changes as we cross the interface. And then we study how the normal component of the field changes as we cross the interface. And tangential component. Oh, the subscripts are E2T and E2N here, and this is E1T, E1N. Okay, T for tangent and N for normal. We need to kind of like assume what is the positive direction and the negative direction. So we use the right-hand rule. We assume that in this direction is T hat and this is N hat. Okay. For the tangential components, we're going to apply the first portion. Second postulate, curl E equals 0. Right, this will be the useful postulate to apply. And in integral form, it's E dot dl equals 0. This is postulate 2. Right, and the trick now is to determine a path. Right, so I have this interface, epsilon1, epsilon2. I take my path to be this loop, this small strip. And I want to make it thin as I can, delta W approach 0, because I want to stay close to the interface. And this is delta L. Okay, so if I apply this, I'm going to have, I'm going in this direction, clockwise. So it's going to be E1T delta L. Right, and then here I'm going clockwise. So here, so this is E1T, E2T. So once I'm going in the same direction of E1T, and then when I go to the other material, I'm going in the opposite direction of E2T. It's going to be minus E2T delta L equals 0. I can divide out delta L, so I end up with the result that E1T equals E2T. The tangential component of the electrical field intensity is continuous across the interface. However, the flux density is not continuous, right? Because the flux density relates to the field intensity with epsilon, right? So although E1T equals E2T, right? E1T is D1 T over epsilon 1. D2T is E2T is going to be D2T over epsilon 2, right? So the field intensity is continuous. The tangential component is continuous. However, the flux density is not continuous because of the different epsilon 1s and epsilon 2s. If epsilon was the same, it will also be continuous. Next, we want to talk now about the normal components. Which, let me do that next time.